So the work I'm presenting today is part of VP4 of CENTRIC in task 4.1 titled Emerging Custom L2 Protocols in Specific Scenarios and Applications, and this task is led by University of Oulu. My name is Septimia Sarbu. I'm a postdoctoral researcher in the University of Oulu, and today I'm going to talk about channel access scheme based on logical inference in AI-merged communication protocols for collaborative navigation. So first, let's have a look at the problem we're trying to solve. What are we aiming to address in communication protocol design? In decentralized heterogeneous AI networking will be the foundation of the majority of 6G use cases. So if we think about a network, a very large number of intelligence agents that have native AI capabilities, so we are thinking about AI communicating with AI in a large network, then if we target improving the current data rates that we have now in 5G, we will increase exponentially the energy expenditure and the need for communication resources. And the question that we are asking, can we develop new communication protocols that only support the transmission of relevant data for the use case that we want to solve? So instead of focusing on developing as high data rates as possible, it would be wiser to save energy and communication resources by focusing on goal-oriented protocols, such that they transmit only small amounts of data relevant to solve the KPIs of the use case. And this is the focus of our work in this project, CENTRIC. First, let's have a look at what is the state of the art on emerging MAC communication protocols. That is the medium access control of layer 2 of the communication protocol stack. We have 2 points of view here. One is from the wireless community and one from the AI community. From the wireless community, reinforcement learning has been used in the references provided in the bottom of the slide to emerge new communication protocols in a classic scenario where base station communicates with user equipments using shared data channels and dedicated control channels. So here, via reinforcement learning, protocols have been learned to improve data rates, and they have been successful for small number of users. From the point of view of the AI community, the focus is to learn goal-oriented communication protocols. For example, we are using here the learning to communicate and communicate to learn paradigm, and the article here in the bottom of the page for emerge communication protocols for collaborative navigation of robots. So robots need to learn a way to communicate with each other to improve or to decrease time to destination on a grid where they are placed randomly and they move taking into account obstacles. So in this case, no wireless infrastructure or no communication infrastructure is assumed, and everything happens in the ideal scenario where there are no channel errors, everybody communicates instantaneously with everybody on the grid, which is not the case in real-world scenarios. So although reinforcement learning has been successful in learning new communication protocols, it has several very important challenges. Firstly, what is learned is not interpretable, and this is a very big problem if we want to deploy these protocols in a real-world scenario. We need to know what they mean to troubleshoot, to debug, and to know where the errors come from when they are deployed in a real-world scenario. The second part is that we don't have scalability. So what I mentioned before, that the reinforcement learning has been successful, but only for very small number of users, which is not the case for wireless communications, where we want to go to thousands of users. And this is because we have a large state and action space in reinforcement learning algorithm, and prohibits the convergence and the learning of the policy there. So we have few devices, it works only for few devices, and we have low sample efficiency, which is another problem. It means that we need to take a lot of samples, and the training takes a very long time to convergence. Another issue that we have here, or we want to exploit for gains, is that general purpose protocols, they work very well in specific scenarios defined in the beginning. For example, the contention-free protocol works very well for homogeneous networks, but when we have for example, a 6G use case or a specific task, a specific KPI we want to solve, they may be suboptimal because they don't exploit the specific features of that application. So in this work, we want to tackle the suboptimality of general purpose protocols, meaning that we want to devise goal-oriented protocols that exploit the specific characteristic of the application for gains. So let's have a look at the system model that we're using. We are enhancing with AI legacy communication protocol of a base station and two UEs. So we have the standard scenario where a base station orchestrates the communication between two user equipments. They share uplink and downlink data channels. Through the uplink, the user equipment send their data to the base station, and through the downlink shared data channel, they receive data from the base station. And it's shared, so we have one data channel for two UEs, and they have dedicated control channels. So the base station tells them what to do via the control channel. But the base station needs to learn the channel access policy to assign the shared channel. Now, those two UEs are replaced with a AI emerged communication protocol from the state of the art. So each UE is a team of 3 agents that need to communicate among themselves to reach the destination. So we have in total 6 agents, and they need to share their data channel. So the base station needs to allocate the data channel wisely such that the KPI of the application is satisfied. For one team of agents, we take the emerged communication protocol from learning to ground multi-agent communication with autoencoders, where I mentioned before, we have device-to-device communication, instantaneous communication, and agents share messages to go faster to the destination. Now, in our application, we use 2 groups of 3 robots, so we extend this concept to 2 teams. Each team needs to needs to reach a destination, a given destination. So we have 2 destinations, 2 teams, and the KPI of the problem is that they need to execute tasks in parallel. For example, this can be encountered in a shop floor. So for example, for collaborative manufacturing, where you have a lot of robots on the shop floor, and each of them, they are in teams and they need to execute certain tasks. In our case, we need that the tasks are executed in parallel, and this is what the KPI of the problem is. So here, if we maximize data rates, this will not ensure that we execute tasks in parallel. So these 2 things are all completely orthogonal. So instead of just focusing on allocating energy and communication resources to maximize data rates, we will focus on creating a channel access scheme that adapts dynamically to ensure that robots reach the destination. The same number of robots from each team are at the destination to execute the task in parallel. So this is the diagram of the communication system, and I will go through an example of how the communication takes place. So the role of the base station is to decide the channel access, to perform inference on the communication messages, and to route missing messages to other agents. So for example, at time step 0, the base station via the control channels, so we have 3 control channels for each team, so 6 robots, 6 control channels, but only 3 dedicated data channels. When one team gets access to the channel, the other one is idle and the robots cannot move on the grid. At time point 1, agents upload their messages to the base station. So each agent has one message, but in order to move on the grid, for example, agent 0 needs its own message, agent 1, message from agent 1, and message from agent 2. And at the other time point, they are received from the base station because the base station has collected everything, so it sends to the agents the missing messages. And then at the third time point, they can step in the environment. So only after they have received all of the missing messages can they go towards the destination. Okay, so now we know the robots, how they move on the grid, but the question is, when do they get the channel access? And this is decided by the base station by processing the communication messages. So since everybody is uploading their communication messages to the base station in time will create a time series of what has been exchanged. And because the communication messages are auto-encoded, they are, so via deep learning, they are states are encoded into communication messages. Implicitly, they contain the domain knowledge, so the position and the goal visibility of the agents. But they are random numbers, so just by inspection, it's not possible to say where the robots are on the grid, but that information is hidden in the time series, and we employ signal processing at the base station to infer when a robot has reached the goal. Because if the base station knows when a robot has reached the goal, it will switch the channel access to the other team. So this is the information that the base station needs. Now that here is this is a figure just to show that indeed communication helps reach the destination faster. So the distance to the goal for other agents decreases faster after at least one agent has reached the destination. And this means that by analyzing the AI merge messages and computing the distance of the agents to the goal, we see that once one agent has reached the goal, the others go there faster. It means that communication enables faster navigation and that the messages indeed contain useful information and they are just not random. What is the solution that we are proposing for the channel access scheme? Because our focus is the wireless communication. So we have four main elements. One is that we propose a multiple access for parallel task execution, not for increasing high data rates. And this is relevant because we are proposing a dynamical channel access scheme that will improve, we will satisfy the KPI of the problem. For this, we use a framework called signal temporal logic for processing at the base station. We also use AI merged protocols, which we embed in a legacy wireless communication system. And by using the signal temporal logic inference, we provide a human interpretable system behavior of the communication messages and of the entire system. So just a brief overview. A signal temporal logic is a logical formula that helps track how properties of the dynamics of a system vary over time. So remember that I mentioned the base station has access or creates time series of the communication messages. And using a logical formula that describes when a robot has reached a goal, using that, it can determine when it is true or false. So when that formula that says when a robot has reached the goal is true in a time interval, then the base station can decide to switch the channel access. So just let's have a brief look at the figure I showed previously, where I show how communication messages vary in time. So the base station has a logical formula, and it checks that formula to see when it becomes true, because as the time progresses, the base station gets more and more communication messages, so more and more information about what is happening in the system. And for example, in this time point here, at some point the formula will become true, so the base station knows that an agent has reached the goal. We use Jain's fairness index to assess the fairness of the system whenever a new robot has reached the goal. Jain fairness index is also used in the proportional fair scheduling scheme, for example. So if this is 1, that it means we have equal number of robots as the destination, which is what we want. Just let's have a look at the experimental results that validate that our scheme has merit and it's a good approach for this problem. So here we compare with the round-robin scheduling scheme. Our scheme achieves a more fair allocation of the channel access time compared with the round-robin scheduling scheme. So in dark blue, we have equal share of resources. Light blue is the round-robin, and our scheme, together with the ground truth, is the closest to a fairness a more fair allocation of the resources. So what happens in the round-robin scheme? It means alternating access to the channel to the two teams, but this will, if we alternate the access, we will not know, we will have no control over how many robots reach the destination, because the robots are placed randomly on the grid. Sometimes maybe they are closer or sometimes further away, and just by switching the channel access will not help us understand what is happening with the dynamics of the system. But in our scheme, which we propose, if we analyze the dynamics of the system by the base station, then it can adapt dynamically to what is happening. So it will give the channel access depending on the condition. So the takeaways of this study that we think is very important is that in order to obtain gains, either in energy savings or communication resource savings, we need to shift the focus from maximizing output to maximizing application-specific KPIs. In this case, the KPI is not a number or not something tangible, but is an idea that we want to have parallel task execution. Another thing is that we propose embedding AI features in traditional MAC protocols, so combining the advantages of both. AI gives flexibility and gives goal-oriented protocols, but traditional communication protocols have the advantage that they scale to very large number of users, and we, by blending these two features or two advantages, we get a better protocol. Another thing is, if we move the processing at the base station, we can scale to very large number of users. And also a main takeaway is that we need goal-oriented protocols to obtain gains and energy savings. Thank you for your attention, and I will take any questions that you have.